Good morning, everybody. How are you? Today is the 18th of February, a few days after Valentine's. The year is 2021. Okay. Today I'm going to continue with second order circuits. This is our session 22. We start the second order circuit with session 20, I believe, right? 20. There was I was talking about the general terms and how to solve the equations, the second order differential equations. Then session 21 was about RLC source-free circuits. So today I'm going to continue with second order circuits, and but this time it's not a source-free because a source-free we need to simplify the natural response. But some of the examples here would include the forcing term in the differential equations. So in session 20, I have written this table up. Okay, it's a way to find a force response, okay, by using the Triforce solutions. So if you have a second order differential equations, right, in this form, your f of t here, f of t is called the forcing term, okay, f of t. When we have source free, or we have to find a natural response, we set f of t equal to 0, right? So this term goes to 0, and then we find a natural response. But if we want to find a force response, we have to include it in there too. And to do that, okay, this is some of the term that you can use. If your f of t is simply a constant, like 5, 20, 48, things like that, okay, then you can try your solution x f of t, okay, f for force, right, the force solutions, as a constant also, a constant a. We don't know what it is yet, but a. If you have your forcing term, just a term t, okay, the variable t, then you try your solution as at plus b. If it's exponential form, e to the sigma t, like e to the 5t or something, you use a e to the sigma t also. Sorry, this is maybe confusing. Take it off. Yes. Okay. Right. So this is t right there. Okay. And if your forcing term, right, f of t is in the form of sinusoidal, either sine omega t, or cos omega t, then this is your Triforce solution, a sine omega t plus b cos omega t. Okay. If it's in the term of the combinations of the product of e to the sigma t and the sinusoidal, okay, sine omega t, or e to sigma t cos omega t, then you try this. Okay, so I'm going to do some example right now of how to do this. Okay, so I'm going to this is an example exercise 1. Let me get my note right here so I can see it closely. Okay, so we have a current source and a simple RLC circuit in parallel, connected in parallel, so they are all connected in parallel, and the source is in the term of 8 e to the minus 2t u of t. Okay, and this is 6 ohms, 7 Henry, 1/42 farad, and we want to find the current I that go through the 7 Henry. Okay, so therefore find so-called I of t. Okay, for I of t. Well, I hope you remember we did the unit step, this u of t right here, which is called the unit step function. Okay, and of course our unit step function is, the definition is, right, if t is less than 0, right, your u of t is equal to 0. If t is greater than 0, your u of t is equal to 1. So in other words, in this current source, it means that at t less than 0, right, it's shut off, right, the current source is shut down, so therefore it would become like an open circuit, and so therefore there's no sources applied to the circuit at all. Okay, and then the switch would turn on, right? And then at t greater than 0, then you start having the current giving out as 8 e to the minus 2t amps. Okay, so therefore, well, we can assume right away that, okay, since when at t equal to 0 minus, right? Well, there's no source connected to it because u of t is equal to 0. So your initial conditions, I at 0, of course, is 0 amp, right? And of course, this is parallel, so we have a voltage here, right? A voltage here, voltage drop. So therefore, there's also no voltage. So v of 0, v at t equal to 0 minus is also equal to 0, right? Well, v is also this v right here, even though I'm, writing it on top of the inductor, it's parallel, right? They are connected in parallel, so therefore it's also the voltage drop across the capacitor. So therefore at t equal to 0 plus, okay, let me move it this way. Sorry, okay. At t equal to 0 plus, right? Then your I 0 plus would be equal to I at 0 minus equal to 0. And V at 0 plus is equal to V 0 minus equal to 0 volt. Okay, so this is your initial conditions. Okay, then of course at t equal to 0 plus, what does the circuit looks like? Well, it looks like exactly what this is. So I'm going to sort of like draw it again. So E minus 2t amps, 6 ohms, 7 Henry, and then the capacitor. So 7 Henry, and you want to find the current right here, and this is 1/42 farad, and this is your V. Okay, so therefore circuit analysis, how does the current flows? So the current flows out from the source, divided into I across R, I through R, not across, and I through the capacitor, right? So therefore, with things connected in parallel, different I into each branch, so therefore we can apply the K, you should think of applying KCL, right, at node V. Okay, so therefore we would be writing, so it's IR plus I plus IC equal to the so-called, let me write IS, right, 8 e to the minus 2t. Okay, so therefore what do? I want to find I, right? So I should try to change everything to I, correct? But let's see, IR, right, is V over R, right? Or I stay as I don't want to change that. And IC is current through a capacitor, so therefore it's C dV by dt equal to 8 e to the minus 2t, correct? Well, how do we change V into the term of the current? Anything. So, okay, V is also V across L, right? And so the relationship between V across L and the current through inductor L is V equal to L di by dt. So I substitute this in wherever there is V is. So therefore, and of course, V over R become L over R di by dt, correct, plus I C dV by dt. So dV by dt would be L d square I dt square. So it become C L d square I dt square equal to 8 e to the minus 2t. So now we have everything in the term of current I. So if I write it neatly in an orderly fashion, so CL, right, plus L over R di dt plus I equal to 8e minus 2t. So therefore, if I divide everything by CL, I would get d square I dt square plus LL cancel out, so you have 1 over CR di by dt plus I over LC equal to 8 e to the minus 2t over LC. If I substitute C equal to 1, so C equal to 1 over 42 farad, L equal to 7 Henry, okay, I would get d square I dt square plus 7 di dt plus 6, oh I forgot I, oh it's I right here, 6I equal to 48 e to the minus 2t. So this is your second order differential equation that you have to solve for I, okay, for the current I. So to do this, right, of course you have to find the natural response, right, natural response, and you have to find the forced response, okay. So therefore, to find the natural response, we have to set your f of t equal to 0, right? So you have to set your f of t equal to 0. So f of t equal to 0. So therefore, you have d square I dt square plus 7 di dt plus 6I equal to 0. Okay. So change that to characteristic equations, right? So it becomes s square plus 7s plus 6 equal to 0. So therefore, s plus 6 times 1 is 6, 6 plus 1 is 7. So s plus 1 equal to 0. So therefore, your roots are s equal to minus 1 and minus 6. So that means it's, distinct, not the same. So therefore, your solution for in of t would be equal to k1 e to the minus 6t plus k2 e to the minus t m's. So this is your form of the natural response. Now come to the forced response. Well, your f of t, since your f of t is equal to 48 e to the minus 2t, right? If you look at the table, we have to try your solutions, right? So your IF of t from the table, it's in a term of exponential right here, right? So it's this term that you have to try. So therefore, I'm going to write it as, well, b e to the minus 2t. Okay, so when I assume that this is my solutions. Oop, low battery. Okay, oh, I hope this lasts, but I'm charging it. Okay, so therefore the IF of t dt is equal to minus 2b e to the minus 2t. I'm doing the differentiations because I'm going to substitute it back into the original equations. So d square IF dt square would be equal to 4b e to the minus 2t. So I will substitute all this back into the original equations right here. So I would have, so therefore it's 4b e to the minus 2t, right, plus 7 di dt, so minus 2b e to the minus 2t, plus 6i, right, 6i is b e to the minus 2t equal to 48 e to the minus 2t. So this is your what you get. Then add the like term together. They are e to the minus 2t and b, right, has b in common. So it becomes 4 minus 14 plus 6 b e to the minus 2t equal to 48 e to the minus 2t. So it becomes, so therefore compare the two together, right? So therefore you would get b is equal to minus 12. That means your forced response for the current is equal to minus 12 e to the minus 2t m's. So put this together, right? Your current, the solution, the complete solution is minus 12 e to the minus 2t plus k1 e to the minus 6t plus k2 e to the minus t m's. Okay, so This is your general solutions. However, you still need to find K1 and K2 to complete your problems. So you have to find K1 and K2. To find K1 and K2, you need the initial conditions. There's two conditions that you need. One is I at 0 because, well, the initial condition start when t, changes at t equal to 0. And another one is the I dt at 0. We already know that I at 0 is equal to 0 amps from the beginning of the problems. But the IDT you have to find it, but okay, you have to try to recall, okay, which formula has the IDT. And this is the current that go through the inductor, right? So therefore, we have said before that, V equal to L di dt, and that's where the IDT, appears. So V across L, right, at 0 is equal to L di dt at 0. Well, it happens that V is the same. This V, the voltage drop across this inductor, right, is also the voltage across the capacitor in the problem. See that here, right here, right? This V right here is the same thing as V across the capacitor. And we have found that the voltage across the capacitor at 0 is also 0 volt. So therefore, when you come back here, right? So therefore, okay, di dt at 0 is equal to V at 0 over L. So therefore, it's equal to 0 amp per sec also. Then, when you get these two initial conditions, you substitute back into your solutions. So the first one is at I equal to 0 is equal to 0 amp. That means T is equal to 0, right? So therefore, this becomes minus 12, right? E to the 0 is 1, plus K1 plus K2. So in other words, you have K1 plus K2 equal to 12. Okay. Another condition is di dt at 0 is equal to 0. So therefore, when you differentiate, I forgot to differentiate it for you, right? So let's differentiate this. Let's see, let's use a different color. So do you think you can differentiate this, right? This become 24, right? This become minus 6. So it become minus 12 times minus 2 is 24 e to the minus 2t. So this is di dt, right, equal to minus 6 k1 e to the minus 6t minus k2 e to the minus t, right? So that's di dt. So when t equal to 0, right, e to the 0 is 1. So this becomes 24 minus 6k1 minus k2. So you get 6k1 plus k2 equal to 24. So you use this to solve for k1 and k2, and you will get k1 equal to 12 fifth and k2 equal to 48 fifth. So therefore, your final answer, I of t, would be equal to minus 12 e to the minus 2t plus 12 fifth e to the minus 6t plus 48 over 5 e to the minus t amps. So therefore, this is your final answer. So you get some ideas, okay, how to solve for the differential equations that have forcing functions. Okay. So next, I would like to do another problems. I told you, I must have mentioned before that the second order circuit, it doesn't generally have to have just R, L, and C. It could be two storage element, that cannot be combined to become single element. So I'm going to give you another example. Okay, this example. Okay. For you to see. Okay. So next example. So in this case, you don't have RLC circuit, but you have two inductors. So two energy storage element. So 8 ohm, 2 Henry, 1 Henry, and 4 ohms. And we want to find I2, which is here. We want to find I2. Find I2 of T given VG is of T is equal to 20 cos 4T volt. Okay, so I'm going to show you this problem. Okay, all right. So as you can see that we have two inductors, and these two inductors, the way they connected, they have 4 ohms right here, right at this point. So therefore I cannot combine if they're not connected directly in series or in parallel, and I cannot combine them to be a single inductor. Okay, so therefore let's see how to find I2. Well, in this case I'm going to use mesh analysis. So this is I1, so this is I2. I'm going to use mesh analysis. Right? Okay. So I'm going to write KVL. When we do mesh analysis, we write KVL of mesh I1. So it's minus VG, right, plus V across 8 ohms. So according to the current I1, so flowing in these directions, right, so this plus minus voltage drop right here, and plus minus and plus minus like this. Okay, so plus V across 8 ohms plus V across the 2 Henry plus V across the 4 ohm equal to 0. Okay, so therefore change that to the in terms of mesh currents. So minus VG plus 8I1 plus L di dt, right? The voltage drop across the inductor is 2 di1 dt, okay, plus 4I1 minus I2 equal to 0. Okay, so I'm going to rearrange that. You get therefore 2 di1 dt plus 12I1, 8 plus 4 is 12, I1 minus 4I2 equal to VG. So this is equation number 1 that we get from mesh I1. Okay, then KVL, write down KVL mesh I2. Okay, so I get according to, let me use red color. So I2, right, according to the current I2 go like this, so you get the voltage drop across 4 ohm like this, and this is the voltage drop across the 1 Henry. So therefore you will get V, right, across 1 Henry plus so-called V across the 4 ohm in red colors, okay, equal to 0. So you will have 1, right, L di by dt, so di2 by dt plus 4 times, well, since the current I2 now enters a positive, so becomes I2 minus I1, right, and I1 goes into a negative terminal of the red color polarity, so this become 0. So you get, well, di2 dt plus 4I2 minus 4I1 equal to 0. So this is equations, well, I'm not going to write that yet. Okay, well, let's see. I got these two terms. Okay, I want to find I2. Somehow I have to change things into I2. So I'm going to write this one right here, right? I want everything in terms of I2, so I have to replace I1 with I2. So from these equations, I can get I1 would be equal to, right, I1 positive, right? Okay, so it's di2 dt plus 4I2 divided by 4. So this is my second equations. This is I1. Okay, and then okay I'm going to substitute I2 into 1 I'm going to substitute okay equation 2 into equation 1 right oh okay the first one is 2 di1 dt oh let me do di1 dt di1 dt will become 1 over 4 d square I2 dt square plus 4 di2 dt okay so therefore substitute it back into equation 1 I would get 2 right times di1 so it's 1 over 4 d square I2 dt square plus 4 di2 dt okay plus 12i1 so 12 1 over 4 di2 dt plus 4i2 minus 4i2 equal to vg so I get these equations okay so I'm going to do the math right do the math well let's see it would become at the end okay so when you do it please do it yourself okay and you will get d square I2 dt square plus 10 di2 dt plus 16 I2 equal to 2 vg okay so this become your so-called if you write it if I write it d square I2 dt square plus 10 di2 dt plus 16 I2 equal to 2 times my vg was 20 cos 4t 20 cos 4t so it's actually 40 cos 4t okay so it's 40 let me write 40 so equal to 40 cos 4t so this is your second order differential equations it also show you that you don't have to have just RLC circuit to have to get the second order differential equations for you to solve okay it could be two of the same energy storage elements okay so therefore now you have to solve for the solution right of course you have to find I2 natural response and you have to find I2 the forced response okay so if you want to find natural response you set f of t equal to 0 right so you have d square I2 dt square plus 10 d I2 well n also so we don't get confused plus 16 I2n equal to 0 change it to characteristic equations so s square plus 10s plus 16 equal to 0 so therefore your s is equal to if you can't do it right away through your head you use the formula the quadratic form to solve so 10 square minus 64 over 2 so it become minus 8 and minus 2 so again distinct root so therefore I2n of t is in the form of k1 e to the minus 2t plus k2 e to the minus 8t m's okay so that's your natural response so for your forced response right so your forced response your force function is in terms of cos right 4t so your try force solutions okay would be in a term of a cos 4t plus b sine 4t m's okay and then you have to substitute this back into this original equations and that could take a while right so therefore if I need both the first differentiate once and twice so I would go and do it so that I have it ready when I want to use it so di2f dt equal to minus 4a sine 4t plus 4b cos 4t, right? You have to use like what a chain rule for to do that. I to f differentiate again would become 16 minus 16a cos 4t minus 16b sine 4t, and you substitute it back. Okay, let me continue here, okay, because it would be, so first one, d square I2f dt square, so minus 16a cos 4t minus 16b sine 4t plus 10 times di2, so dt, so minus 4a sine 4t plus 4b cos 4t plus 16 I2, so 16a cos 4t plus b sine 4t would be equal to 40 cos 4t, right? So I think you can cancel some of them out, right? Like for example, this minus 16a cos 4t and plus this one right here, so out, minus 16b and plus 16b and 16, so this is also out, right? 16, so you work it out, okay? Now I'm getting confused too, but when you expand it out, you can cancel it out, so therefore you will get at the end 40b cos 4t minus 40a sine 4t equal to 40 cos 4t. Okay, so you compare the left hand side, right? This is the left hand side term, should be equal to the right hand side term. Okay, so if you can see this, the cos, right? So 40b cos 4t equal to 40 cos 4t, so therefore you get b is equal to 1, right? Whereas the sign on the left, there's a term on the left, but there's no term on the right, so we can assume that a also is equal to 0. So therefore your I2 f of t consists of only it was a b, so you have b equal to 1, right? So you have only sine 4tm. So therefore your solutions I2 of t consists of the sum of the natural response and forced response, so you get sine 4t plus k1 e to the minus 2t plus k2 e to the minus 8tms. Okay, in this case I'm not going to work on, because we weren't giving any sort of initial conditions, so and I'm going to leave it right there, because this question is to show you how we don't need to have RLC circuit to get the second order differential equation to solve. Okay, the next one I'm going to go on to step by step. We also have a step by step for the second order circuit, but it has to be the forcing term has to be a constant value, so we have to have independent source there. So there's step, I'm going to write down the general second order circuit steps, okay, having one or more independent source with constant values. It's like we have DC. It's like we're dealing with DC circuit. Okay, so step 1. So similar to the step response for the first order circuit. Okay, but it would take a little longer. Okay, so step 1. Okay, we have to determine the initial condition of the solution that you want to find, x0, and of course there's two of the initial conditions, that is the x of t and dx dt at 0, assuming that the switch changes at t equal to 0. You also need to find, the final values. So x at infinities. Step 2, you find the natural response. Xn of t, right? By setting all the sources off. So in other words, your forcing term is set to 0. Also find, the second order. Find the, I think I got it switched, sorry. So this is find initial values, right? So you have to find at t equal to 0 plus, right? You have to find your second order circuit, your second order differential equations. Then from this one you have to find the natural response. You have to find the natural response. You find the roots. You set f of t equal to 0, find the roots, Then step 3, obtain force response. In this case, your force response, if it's constant values, you have your f of t as a constant values. Your xf of t, your force response, is nothing but your final values, the final values. Then step 4, your general solution, your total solution is x of t equal to xf of t plus xn of t. Then step 5, you have to find the constant in your solution. Find constant. You can okay, let me rewrite. I think my handwriting is getting too tangled up. Find the constants, from the initial conditions that you have found in step 1. And I'm going to do one example for this. Let me find, where's my example? Okay, you get all this down. I'll give you a few seconds, to that. All right. Well, of course, you can always stop, later on, stop and pause, to write it all down in your own note, please. And also, I would encourage you to actually write it down on your note, what I have taught, because otherwise you'll forget. And you can't, when you have to study for your exam, you can't just go back to all my, play everything back again. It's a waste of time. It's faster to look through your notes. So therefore, the example, find the complete response for V. For V of t. Let's see. And then, to challenge yourself, and then find I of t. For t greater than 0. So here is the circuit. 12. So the source is 12 volt, constant values, DC value. So 4 ohms. 1 Henry, 2 ohms, T equal to 0. And this is the voltage drop across this capacitor. Okay, and the current I is here. Okay, current I is there. So I'm going to do it, try to do it like step by step from above. Since we have a constant values, so I'm going to use step by step approach. Step 1. Find initial values and final values. Find initial and final values. Alright, so initial values mean well the switch changes at t equal to 0. So I have to check first before the switch changes, is there anything stored in my capacitor and in my inductor, right? And to check that, for the capacitor, we check whether what's the voltage, is there any voltage there? For inductor, is there any current, in through the inductor? So I'm going to draw, so at t equal to 0 minus, so what does this picture looks like? The switch still open, so plus 12, right? Assuming that it has been, it has reached steady state by the time at t equal to 0 minus, so inductor acts like a short, right? This is open, right, because the switch was open, okay? And the capacitor, of course, would act like an open circuit. So this is your V and this is your I. Okay, so looking at this, right, current cannot flow because this is all open, right? Open. So current cannot make a complete path. So therefore, your I at 0 minus is equal to 0 amps. And V at 0 minus then, right? Since there's no current flow, there's no voltage drop across this 4 ohm. So that means this point here is nothing but this point. And this terminal here is this terminal. So it's 12 volt. So 12 volt. Okay, that's initial values. So therefore, then what is another one that we have to find? We have to find V first, correct? So another initial values that we need to find is we need to find dV dt at 0. That's another one. Okay. So then at t equal to 0 plus, right? We know that, well, V at 0 plus equal to V at 0 minus equal to 12 volt. I at 0 plus equal to I at 0 minus equal to 0 amp. Not because, please remember, I at 0 plus equal to I 0 minus. It's not because this current passed through a resistor, okay? It's true only because this current also passed through the inductor, an inductor. That's why it's true, okay? So therefore this capacitor and this is for the current through inductor, okay? Then we have to find dV dt, right, at 0. So let's see, so at t equal to 0 plus, okay, let's look at the picture, the circuit. Okay, the switch closed this time, already closed, and we have a capacitor like this, okay, and this is my I, and this is, of course, V, right, and we have a current, of course, go through here, IR and IC, okay. So therefore, if I write, let's see, KCL here at this point, so I at 0 plus equal to I that go through the capacitor at 0 plus V0 plus over 2 ohms, right, IR, so 2 ohms. So therefore, I at 0 plus is 0 equal to C dV0 dt, because we want to find dV dt, right? And that formula, that term is in the formula of the relationship, okay, of the current across capacitor and the voltage drop across the capacitor. So plus V at 0 plus is 12 over 2. So therefore we get dV0 dt equal to, right, minus 6 over C, which is a half, right, 0.5. So 0.5. So therefore minus 12 volt per second. So this is our dV dt. Okay. So this is our second initial conditions. Then find the final values. So V at infinities. So what does the circuit looks like at infinities? So at t equal to infinities, we have plus minus 12, right? It's this circuit, but has been like this for a long time, reaching steady state. So again, right, this acts like a short, and the capacitor acts like an open. So this is V at infinities. So look at this picture. V at infinities is nothing but V across the 2 ohms. And the way the current flow, it flows out of the 12 volt, go through 4 ohms, right, and go through the 2 ohms like this. It's just one loop. So therefore, having things connected in series, you can use voltage dividers. So therefore, it's equal to 2 over R total is 4 plus 2 because they are connected in series, and divide, and this 2 voltage drop across the 2 ohms divided out from the 12 volt. So therefore it becomes 4 volt. So this is your so-called final values V at infinities. Then step 2, we just did step 1, no? So step 2, we have to find the natural response. Find Vn of t. Find the natural response. So let's draw the picture again. Oops, what happened? Please, when you redraw your circuit, make sure that you sort of, if you're not fluent in analyze a problem, try, please just copy everything, the voltage drop, the polarities. Now make sure you get all the information onto your diagram, onto your circuit that you redraw, okay, and correctly too, okay. So again, I'm going to, so this is the current IC, okay. So I'm going to, we want to find V, right? So V is somewhere with the capacitor and capacitor. This voltage drop across the capacitor and these 2 ohms. So I'm going to write KCL at V. Okay, node V right here. Okay, so therefore it's, let's see, this I, right? See, I didn't write it completely also. So I equal to IR plus IC, right? This is IR, I across the 2 ohms. So therefore, you will get I equal to V over 2 plus 1 over 2 dV dt. So this is equation number 1. See? Then, let's see, I'm going to write down KVL, okay. KVL for this mesh right here, okay. So I will get, well, the current go through this direction, clockwise direction, so plus minus, voltage drop plus minus, right? And of course we have V right here, so we have 4I, right, plus V across this 1 Henry is L di by dt, so 1 times di by dt, and plus V, okay, we want to find V, right, so I want to keep V, so plus V, right, and then minus 12 equal to 0. So therefore you have 4I plus di dt plus V equal to 12. Okay, so this is equations number 2, right? Well, I want my equations to be in terms of the voltage because I want to find V of t, the voltage, right? Voltage V. So I'm going to substitute 1 into 2, equation 1 into equation 2, right? So I would have 4i, which is V over 2 plus a half dV dt plus 1 di dt, right? dt of V over 2 plus a half dV dt, right? Plus V equal to 12. So have to do the math thing, right? You get 2V plus 2 dV dt plus a half dV dt plus a half d square V dt square plus V equal to 12, right? So multiply everything by 2 and sum it all and rearrange it, then you will get d square V dt square, right, plus 5 dV dt plus 5 dV dt, and then plus 6V equal to 24. So you get this second order differential equations, and then you have to find the natural response Vn. So to do that, you set f of t equal to 0. So therefore, to find Vn of t, right? Then you have to solve d square Vn dt square plus 5 dVn dt plus 6 Vn equal to 0. Change it to the characteristic equations. So s square plus 5s plus 6 equal to 0. So therefore, your s is equal to 3 times 2 is 6, right? And 3 plus 2 is 5, so it works out. So s equal to minus 2 and minus 3. Okay. So therefore, UVN of t is equal to a e to the minus 2t plus b e to the minus 3t volt. Okay. Then step 3, it says that your forced response, is that right? Your step, let's look. Step 3, obtain forced response, and your forced response is simply the value at t equal to infinities. So step 3, your Vf of t is equal to V at infinities. So therefore it's equal to 4 volt. So at the end your answer is V of t equal to 4 plus a, well I'm right like this, so equal to Vf of t plus Vn of t. So therefore your V of t is equal to 4 plus a e to the minus 2t plus b e to the minus 3t volt. So this is your general solutions, right? And then step 4, or no, this is step 5, right? So this is step 4, and step 5 you have to find the constants a and b, right? Find a and b using initial conditions that you have found in step 1. So therefore, okay, so first your V of t is that, so your dV dt is equal to minus 2a e to the minus 2t minus 3b e to the minus 3t. Okay. So substitute at t equal to 0. V at 0 is equal to 12, right? So t equals 0, so it becomes 4 plus a plus b. So therefore, a plus b is equal to 8. And the second initial conditions, dV dt at 0 is equal to minus 12. which is equal to minus 2a minus 3b. So you have 2a plus 3b equal to 12. Okay, so solving these two, you have a equal to 12, b equal to minus 4. So therefore, your final solution for the voltage V is 4 plus 12 e to the minus 2t minus 4 e to the minus 3t volt. So that's it, right? Final answer. But the question also asks for the current I. The current I. If I draw the circuit again, right? Real fast, right? So this is I, this is IR, this is IC, and this is V. So therefore, you can find I, correct? Because we have started that, what? I is equal to IR plus IC, right? So I is equal to V over 2 plus C dV by dt. So therefore, just do it, right? So C is a half, so therefore I of t is equal to V of t over 2 plus a half dV of t dt. And your V of t is that, right? So therefore it becomes, so therefore I of t, divide everything by 2 on the first term right here. So it becomes 2 plus 6 e to the minus 2t minus 2 e to the minus 3t, right? Plus a half, you differentiate things, right? Differentiate the v, right? So it becomes minus 12 e to the minus 2t plus 6 e to the minus 3t amps. So therefore, I of t become 2 minus 6 e to the minus 2t plus 4 e to the minus 3t amps. So this is your current I. Okay. So that's one of the example. Okay, using step by step. But I think this is for today. All right, it has been a while now. Okay, so let's take a break and I see you next sessions. Bye.